and pore water pressure. So you can write it down. So we are in the middle of what? We are in primary consolidation. We have discussed immediate settlement, then number two, primary consolidation. Then in primary consolidation, we will be discussing about effective stress and pore water pressure. And then we will go to secondary consolidation. You should also like remember that primary consolidation is also called as 1 degree consolidation, and secondary consolidation is also called as 2 degree consolidations. Okay, so primary consolidation is called as 1 degree consolidation. You can write it down. And secondary consolidation will be called as 2 degree consolidation. So I hope I am clear. And now let us talk about effective stress. Now, you see, when you talk about effective stress, there is a, a way of understanding about the effective stress and pore water pressure. The way is developed by Tarzaghi. Okay, this Tarzaghi, may I know, like, if you have heard his name Tarzaghi before? Type Y if you have heard the name of Tarzaghi before. Okay, so today is the official introduction of Tarzaghi with you. Okay, so Tarzaghi is one guy who has developed a lot of formulas. And as you like proceed with geotechnical engineering, you will see that Tarzaghi, this guy is everywhere. Okay, everywhere he has developed some formula, he has given some recommendation, he has given some assumptions. So he will not leave you. This guy will not leave you. He is a very like he is the most known person in geotechnical engineering. Okay, later on when you will be discussing when you will learn about foundation design, like design of pile foundation, design of footings, design of foundation means design of structures which are below ground, design of substructure. You will see that this Tarzaghi is there everywhere. Okay, so he is one of the pioneers of geotechnical engineering. So from now onwards, like he is officially, he has, you have met him, and at one point of time you will get bored of this guy. Everywhere you will see his name. Okay, so this is the beginning for you all. Okay, so this is the beginning. So now he developed one way of determining the effective stress and pore water pressure, and actually understanding the effective stress and pore water pressure, and that is called as spring analogy. Okay, so generally it is called as Tarzaghi's spring analogy. Okay, so what happened is, I'll take a new screen. Suppose there is a soil sample. Okay, suppose there is a soil sample, and the water level is suppose still here. Okay, of the soil sample, suppose the water level is still here. Okay, and use a piezometer, okay, if you use a piezometer gives us what? Can you tell me? Piezometer, what does it give? Can anyone tell me? What do we find out by using piezometer? Anyone?
Pressure.
What?
Pressure of
Okay, okay,
liquid.
okay, fine, fine. So now, suppose this is the H1 for the water, okay, and suppose we have given one stress, okay, and this whole is the soil sample. I want to ask you if the visuals are clear to you, like if the visuals are like proper. Okay, thank you. So if we give a stress like this, if we apply a stress sigma, okay, then what will happen? This this piezometer reading, initially it will be H1 because it is related to the water. Okay, now it will reach somewhere like H2. It will not reach, I'm saying that it will move by around H2 when there will be some external pressure applied. So in this piezometer, the reading will become H2 when there is external stress applied. Then, so and soil will the soil particles will try to occupy new positions. So these soil particles, obviously, when there is stress, they will try to rearrange themselves and occupy new positions. So that you can write that line. You can write. Okay. So till here, I hope I am clear. Anyone having any doubt, please don't wait. Okay, ask me instantly. Okay. So now soil will try to occupy new positions. Like obviously, if there is no air, then there is no volume change because volume change happens initially due to expulsion of air. So if there is no air, no volume change. Soils will try to rearrange themselves. That's all. So that is the first thing. Then initially, when this stress is sigma, which is applied, it will be taken by the water. This sigma applied will be taken by the water. First step, not by the particles. Okay, taken by the pore water. That is the first step. I'm repeating once again. If you have any doubt, ask me instantly. You can directly unmute and speak up. Okay. So uh, first of all, when we give the load, the stress will be taken by the water at first. Okay, so like the water is saying to the soil particles, okay, the water is telling the soil particles that you take rest, let me handle it. Okay, so the water is telling the soil like that. So let me handle the stress for now. Okay, so water is taking the first step. Then I want to like explain it in this page itself because when you have the diagram in front of you, then it's very good to relate. So now, so water has taken the stress, okay, and this will happen in clay soils. water will take the stress in clay soils because at the very instant, at the very beginning, water will not go out of clay soil because water is what is packed by the clay soil. If the soil is cohesionless, if the soil is sandy, then water will not take the load because water will flow out in an instant. Just remember that. If there is sandy soil or gravel or any cohesionless soil, then when you apply sigma, the water will not take the load. It will flow out directly. But in clay soil, the water cannot move out at an instant because in clay soil, the permeability is very low. In clay soil, the permeability is very low. So water cannot move out instantly. Water cannot move out instantly. Like sands. Okay, I'm giving example of sands. Okay, so like sands, water cannot move out instantly. Let me erase this, otherwise you will get more confused. So in clay soils, just remember that water cannot move out instantly, but in sands, water will move out instantly. So in sands, water will not take the load. But in clay soils, water cannot move out, so water will remain there. And since it is remaining there, it will take the load. So that's why we say that this phenomena happens in clay soil. Okay, so in clay soil, the water will take the load at first. Now, let me again erase this. Now, initially, how much load the water can take? Initially, what was the pore water pressure? Pore water pressure. What is the pore water pressure which is present initially? Pore water pressure which is present initially is height of water into unit weight of water. That is the pore water pressure initially in the soil. Height of water into unit weight of water. That is the water pressure. So water will be giving this pressure. This pressure is related to water. That means this is the pressure related to water. But now, when you apply sigma, when you apply this sigma value, it may be assumed that it is higher than this H1 into unit weight of water. So ultimately, what will happen? The pore water pressure will rise because we are applying some load, some extra pressure, sigma. Okay, so if I write it down, okay, let me take a new screen. It does not provide me enough space in the previous screen. So we can write that initial was H1 gamma what unit weight of water. Initial pore water pressure is H1 gamma water. Okay, then after we apply sigma, after we have applied sigma, after sigma is applied, after a stress of sigma is applied, then the pore water pressure will rise because now the water will be taking more pressure. And how much pressure will rise? It will rise by H1 gamma water plus sigma because additionally we have applied a sigma stress. So initially the pressure of water was H1 gamma water. Okay, then we have applied additionally a stress of sigma. So the since the water is taking the whole pressure, so this pressure will be added to water, because the water is telling the soil particles that wait, I am handling it, I am handling it. So water is handling it. So that's why the pressure of water will become this one, H1 into gamma water plus sigma. Are you clear till now? Are you clear? You can type C also, no problem. Okay. So what is your next class? Next class, can you tell me? MM. I don't know so much of code. Please tell me the.
Mechanics of material.
Okay. So you could have write MOM. Then I could have guessed. Okay, fine. Fine. I will end at 10:10. I will take this 20 minutes more. So here the water pressure is now increasing to this one. So just wait a minute. Just wait. Sorry for that. Okay. Uh, Now this H1 gamma water plus sigma, we can denote it as H2 gamma water. Sorry, this the pore water pressure will rise. This we know, and this H2 gamma water is actually sigma. I'll just erase it because the pore water pressure has risen. If you remember, the pore water pressure has increased by H2, and H2 was actually due to what? If you just see the previous, if you see the diagram in your copies, I hope you have drawn it. This H2 gamma water, it is increase. It is this H2 is increasing because of this sigma. So this sigma is actually this one, H2 gamma water. Okay, so that is the concept that you need to understand. So the water in piezometer has risen by H2 only because of this sigma. That's why we are saying H2 gamma water pressure is equal to sigma. Okay, so there is ultimately a pressure gradient. Ultimately there occurs a pressure gradient. Gradient means like pressure difference. Okay, pressure gradient is established. That means some pressure difference is established actually. So when there is a difference of pressure, the water flows. Water flows if there is a difference of pressure. Initially, the pressure was H1 gamma water. Okay, now it became H1 gamma water plus sigma. Okay, so ultimately there is a difference of pressure. So when there is a difference of pressure, water will now start flowing out, because water will not remain in the soil forever. Okay, so now water will start flowing. Just remember that instantaneously water will not flow out in clay soil. So that's why water will take all the load. And then when there is difference of pressure that is developed, then water will now start moving out. Water will now start moving out. Please tell me if I am clear. You can write either C or Y. Thank you. Thank you for the responses. So now water will start moving out. And now the important point. So there is a difference of pressure. Water will start moving out until the water, until the pore water pressure actually. Wait, just until the pore water pressure can comes down to means initially this was the pore water pressure, then it increased. So when it increased, so the water started going out until the pore water pressure again came back to H1 gamma water. So the pore water pressure will ultimately try to regain its original value. Okay, until then the water will start moving out. And when the water starts moving out, what will happen? The volume will decrease. Okay, so when the water is starting to move out, then soil particles will come closer. Okay, so there will be volume change. Okay, am I going slow or fast? May I know? Am I going slow or fast or like steadily? Can you tell me either? Then I can check on my speed.
Yes, fine, sir. You're going steady.
Thank you, thank you, thank you very much. Okay, so now there is a volume change. There was a difference of pressure. Water started to move out until it will reach its fellow H1 gamma water. So water is moving out, soil is coming closer, there is volume change. So when the soil will come closer, then the effective stress increases. So that you can write. So when the soils are coming closer, soil particles are coming closer, then effective stress increases. Okay, then settlement happens. Same as volume change, same thing. Settlement takes place. So basically, this settlement, this volume change, volume decrease, it's ultimately happening due to what? Expulsion of water. So now let us go back to the equation. Total stress is equal to effective stress plus pore water pressure. Effective stress is denoted by sigma bar. Pore water pressure is denoted by uh, what? The pore water pressure is denoted by small u. So what happens is uh, That is, this one is the applied stress. Okay, so now at the very instant, this equation, now try to please concentrate on this equation, and uh, I'll recommend you to take a minute and just go back to the discussions, whatever we have done till now. Just go back, especially to the just the recent discussions. Just go back. I'm giving you exactly a minute. Okay, I'm looking at my watch, and exactly 1 minute I'm giving you. Then you revise, and then I will relate to this equation. 30 seconds. Okay, so shall I continue? Type Y. Shall I continue? Okay, so now what happens is, related to this equation, when we apply this stress just at the instant t is equal to 0, initial, very initial point, t equal to 0, we have just applied the stress. So the water will take the whole stress. Water will take the whole stress. So at t equal to 0, this effective stress is 0. And you will take the whole stress. This water will take the whole stress at the very instant. Okay, you will take the whole stress. Then what will happen? Then there will be some pressure difference. As I have told you, there will be some pressure difference. I think someone is not muted. Some hissing sound is coming. I don't know from where. Somewhere some hissing sound is coming. Okay, no problem. Maybe some technical issue, I don't know. So water will take the whole stress. Okay, so at the very instant, this effective stress uh, is 0, we can say. Okay, and then at the very end, what will happen? Water will start moving out, and you will start decreasing. Then you will start decreasing. You will start decreasing because water will start moving out. U is the pressure taken by water. Okay, so you will start decreasing, water starts moving out. Okay, so then if you imagine at the, like, after a long time, uh, when no water is left, imagine no water is left, then what will, if there is no water left, then what will be the value of U? Can you write down in the chat? After a long time, if there is no U, what is the, if there is no water, then what is the value of U? Can anyone tell me? If there is no water, all the water is going out. Zero, yes, correct. So there is no water, so there is no U. So after a long time, so no water, so U becomes zero. Okay, so what will be the effective stress? So the effective stress at the final stage, effective stress is equal to total stress. That means uh, ultimately what? Effective stress is given by what? The soil particles, isn't it? I have given you in the previous class. Effective stress is taken by soil particles. So ultimately, logically speaking, no water is there. So the total stress is ultimately taken by the soil particles, which is effective stress. So logically speaking, initially water takes all the stress, so soil particles will not take all the stress at the very instant. So soil particles take zero stress, water is taking whole stress. At the end, water is not there, so water takes zero stress, and soil particles take the whole stress. So am I clear till now? So okay, I'm glad you have understood it. So that is the concept. The final concept you should take home is that at the beginning, pore water pressure takes the whole stress, effective stress takes zero. At the end, effective stress takes the whole stress, pore water pressure takes zero. So that is the thing that you should take home. Okay, so okay, let us end this here, end this discussion here. Enough for today. And tomorrow, not tomorrow, in the next class, I will complete the third part. Okay, secondary consolidation. I will be completing it. Today, there will not be enough time to complete the secondary consolidation. It will take some amount of discussion, so it cannot be done in 5 minutes. So, thank you very much for your patient listening. Thank you very much. We can end this meeting.
Thank you, sir.
Thank you. Thank you.